Hello, everyone. Welcome to the Electrochemical Colloquium. And today we're discussing dynamic instabilities in electrochemistry. So such instabilities can lead to waves and oscillations during the reactions. And of course, they can play an important role in various electrochemical systems, including electrocatalysis and battery materials and many others. So understanding this phenomena is vital when you work or when you want to optimize the electrochemical devices, or for example, interpret the behavior of very complex nonlinear systems. And our today's speaker is Professor Katharina Krischer, who is a renowned expert in chemical physics and non-equilibrium processes. So Katharina received her PhD from Fritz Haber Institute in Berlin and did her postdoc at Princeton University in the United States. And in 1998, she became a group leader at the Fritz Haber Institute. And then later in 2002, she moved to the Technical University of Munich, where she's been a professor of chemical physics ever since. So Katharina, thank you so much for joining us today. Now the stage is yours. Feel free to start at your convenience.
Okay, thank you very much, Andrew, for the nice introduction. Yeah, you have heard that I've been studying dynamic instabilities since quite some time, actually since decades. I did my PhD in the early 90s, and I didn't start with electrochemistry in my PhD. I did it with Professor Ertl, who was working in surface science and in heterogeneous catalysis. And he had an oscillating reaction, the famous C oxidation on platinum, but in the under UHV conditions. And my topic of the PhD was modeling these heterogeneously catalyzed oscillations. But at the same time, I mean, Professor Ertl just entered or came to the Fritz Haber Institute. There was still some overlap with Professor Gerischer, who is essentially the founder of photoelectrochemistry and a very famous electrochemist. And at some point, he came into my office and showed me some oscillating current time series. And he asked whether I would like to work with him together on the problem of modeling his electrochemical reaction. And I said, yeah, sure, seems to be interesting. And I looked at his experiments that he was doing at that time with a technician together. And I was very astonished when I saw the experiments. I mean, you should understand, having a surface science background, you think of very well prepared surfaces, single crystals, and every facet having a different reaction rate, and determining the behavior, and you have active sites, which are important for the reaction rate. And then I saw his experiment, polycrystalline platinum wire, bent to some helix. And so it should be completely heterogeneous. And from my feeling, the reaction rates should be different at every microscopic slice of the area, but yet the global signal was beautiful periodic. And in my opinion, the heterogeneous reaction rates should lead to different oscillation frequencies and different phases. So I could not understand why the mean field signal was periodic, or was very interested in it. So I went into the literature, and I did a literature research, early 90s. And there were just the first papers coming up with some explanations of oscillations in electrochemical systems. So there were probably, let's say, a handful models or electrochemical systems that were understood, but about 800 or 900 citations, all of them report phenomenologically oscillations in electrochemical systems without any deeper understanding. Okay, I thought, this is a great topic to work on, where you can do a lot. And so this was my starting point. And I then slowly switched into the electrochemical systems. And now let me show you my, or explain you what is behind in the background. What you're seeing here is actually a part of an electrode surface of a silicon wafer that is covered with an oxide, and roughly you can say that the pseudo color symbolizes the thickness of the oxide. And you see that here we have very uniform conditions, and this is actually a snapshot during an oscillation. And you see that also these, in this dissolution reaction, you have beautiful homogeneous surfaces, really. So the idea that a uniform or a simple periodic oscillation should have a uniform formally reacting electrode is perfectly met here. And the question why the electrochemical oscillations do often exhibit uniform oscillations, I'll discuss with you. However, they don't need to do so. And here is another example which shows the same reaction, just a little bit different applied potentials. And you see that now the uniform or the surface exhibits some type of spatial temporal turbulence. And this is how I originally, on a microscopic scale, imagined the electrode to be, which is not the case. But you can see here that things can become really complicated or again astonishing. Why is this astonishing? Well, we have here a rather, different reaction rates or turbulent phenomenology of the oscillations, yet the current oscillates rather simple periodically. And so it's also not true that a spatial temporal turbulent behavior needs to lead to some noisy or steady behavior. And I will discuss with you now essentially two parts or two aspects. First, why is it that so many electrochemical reactions oscillate? This is by far more often than in chemistry, chemical systems, and by far more often than in heterogeneous catalysis. So there must be something special in electrochemical systems. This is the first part. Why do they exhibit so easily dynamic instabilities? And in the second part, I will discuss the question, why are the oscillations often uniform, and under which conditions do we expect patterns, and which type of patterns emerge, and what is a driving force for the emergence of the patterns. Here I show you three further examples, rather arbitrarily selected, because you know that most electrochemical systems oscillate. So here I have an example of the hydrogen peroxide reduction on the platinum electrode. Actually, this reaction was intensely started by Nakato and co-workers. And the very nice aspect here is that they found actually 5 different regions of oscillations where 5 different oscillatory mechanisms are behind. So it's not that one reaction should always show the same type of oscillatory mechanism. And I hope that what you understand better in the course of my talk, what I mean with oscillatory mechanism. And on this sketch, you see 2 regions of potential where the system exhibits oscillations. Then I show you an example, I think here, of a wave pattern, which was observed during the CO electrooxidation. On a platinum surface, the pseudocolors here denote the CO coverage, and you see that there are certain fingers which form on the electrode, which travel on the electrode, which can split, and these are the reactive parts of the electrode. Everything else is inhibited, so this would be an example of wave, and here's an example of a chaotic system, and here irregular time series of the current has been plotted in a certain way, that you take the current, the measured current at time t, and plot it against the measured current at some delay time. And you see here a beautiful chaotic attractor emerging. And this is work by Istvan Kish and co-workers. Okay, now, before I end really with my introduction, I think it's also worth having a look into the history of electrochemical oscillations, and also from the history can anticipate that in electrochemistry, instabilities form more easily than in other chemical systems. And the first reports actually go back by 200 years. They're from 1828. And these are the first reports of oscillations in chemical systems at all by Fechner, and he looked at metal dissolution. The first waves on the electrode surface were described by Joule, the famous Joule, shortly about 16 years after Fechner's observation. And then there was a period between 1900 and 1940 where also very remarkable research was done on electrochemical instabilities. Ostwald, a great physical chemist, also observed electrochemical oscillations, mainly during metal dissolution reactions. And he had the idea that these electrochemical waves could have similar properties to the nerve impulse propagation. So he initiated activity waves, for example, on a passive iron wire, and looked then at the interaction between these activity waves or activity pulses. And this is an idea that is the basis of the research on nonlinear dynamics, namely that there are universal laws which appear in systems from completely different disciplines and show you the underlying mechanisms that give rise to certain patterns. And so this was much ahead of its time. These studies were continued in the 40s and 50s by Bonhoeffer and Frank, and also they were much earlier. The studies on chemical oscillations, like the Bézier reaction, for example, started essentially in the late 60s, 70s, and then there was a lot of activity in the 80s. So these are very remarkable early works on oscillations in electrochemical systems and in a framework that has been shaped only 70 years later when the nonlinear dynamics really arose as a field. Okay, now, why do electrochemical systems show so easily instabilities? Well, it's shortly before Easter. If you don't want to wait until the end of my talk, here is a very short summary of the reason. It's an interplay between the electrode kinetics, transport processes, and the electric circuit. So you have mass balance and charge balance equations. If you compare it to chemical systems, you only have the mass balance. You only have the chemical kinetics, heterogeneous kinetics and catalysis, and possibly transport processes. But in electrochemical system, the electrical circuit really helps a lot and is responsible for most destabilization of electrochemical systems. So when we describe our systems, we have the chemical concentrations or chemical variables, and in most parts also the electrode potential as an essential variable. So with other words, we have to take into account the complete electrochemical system and cannot concentrate on the electrode kinetics when we want to understand dynamic instabilities in electrochemical systems. Oops, now okay. Let me get back to my pointer. Okay, so I said the electrochemical, the equivalent circuit of an electrochemical, no, sorry, I said the electric variables are important, and to get the equation of motion for the electrode potential, we look at a very simple circuit for our electrochemical cell. So we suppose we apply constant voltage between working and reference electrode. So this should be the position of the reference electrode. Then we can describe the interface by a parallel connection of a capacitor and some Faradaic impedance. And we have an ohmic resistor, which presents the uncompensated resistance in your electrolyte. This can be easily put in the evolution equation for the electrochemical potential. And I'm always thinking of electrochemical potential drop across the interface and denote this by phi dl. So phi dl is always the quantity that determines the rate of the electrode kinetics. So the currents through our interface, the capacitive current and the reaction current, have to be equal to the current through the electrolyte up to the working electrode, which is simply given by the potential drop across the electrode divided by the uncompensated resistance, R omega. Somehow my keyboard does not respond. Okay. The first thing, if you have set up an equation on linear dynamics, what you do is you look at steady states. So to obtain the steady state is very easy. You set the temporal derivative to 0, which means that we look for conditions where our reaction kinetics, which depends on phi dl, on the electrode potential, is equal to the load line, and we can do this graphically. And I chose here some condition where the electrode, where the dependence or the current electrode potential characteristics shows different regions with a positive and a negative characteristic. And the load line is shown in red, and we see we have 3 intersections, so 3 steady states. Next thing you do in an analysis of a dynamical system is you look at the stability of the steady states. And how do you do so? Well, for small perturbations, you can linearize your equation because, as you know, the expression for the dependence of the reaction rate on phi dl will be, in general, non-local, but for small perturbations from our steady state, the perturbation of the steady state is here denoted by this tilde. We can linearize our equation and obtain the following expression, that a perturbation from our steady state will change according to the change of the Faradaic current with a phi dl at the steady state, plus 1 over r and our linear term in phi dl. This is nothing else than 1 over the Faradaic impedance of the reaction. Okay, and we have a linear reaction, linear equation in phi dl, differential equation in phi dl tilde in our perturbation, which we can solve. And it's clear that depending on this sign in here, we have either an exponential growth of our perturbation, or the perturbation is damped when it stays negative. So our steady state is unstable if this term within the brackets is negative, which means, translated in physical terms, that we need a negative differential Faradaic resistance. And this is the part where the current decreases with increasing electrode potential. And we need some cell resistance. And the cell resistance has to be larger than the absolute value of the negative differential Faradaic impedance. These are the 2 conditions that your steady state is unstable. Okay, now I should mention that what did I assume so far? I assumed that I can describe the dynamics just with one equation, just with the electrode potential. This assumes that all the other quantities, which will also change, like a concentration in front of the electrode, the state of the electrode, maybe perhaps it oxidizes, is fast. It's very fast, so that when you change the electrode potential, it adiabatically adjusts. And then it's sufficient to work with the equation with your electrical circuit I introduced so far. Okay, obviously, we can have our first instability in a system which exhibits I-UC or I-phi-dl characteristics as shown here, which has a shape of an N. And for this reason, these systems are called N-NDR systems. Okay. Now, what happens when we change the parameter? One thing you naturally change is U. And in order to translate this curve into a current voltage curve, you have to realize that we have to add the IR drop to each point, which means we have to add a large IR drop to where we have a large current and a small IR drop where we have a small current. And this leads to the folding of your current potential curve and gives rise to bistable behavior. So in the experiment, what you observe when you have such an underlying current potential characteristics is that you have jumps from a high current level to a low current level and a hysteretic jump from the low current level to the high current level back. So this would be a bistable behavior with two stable steady states. Here we have our positive Faradaic impedance and an unstable steady state in between. The locations at which these jumps occur are so-called saddle node bifurcations. And you can see that at these points, we go from a region where the system has three steady states to a region where we have just one steady state. And so two of them become identical and merge. And at this point, the exponent becomes 0. And this is exactly the condition for a saddle node bifurcation. So in nonlinear dynamics, you would call this transition between our two branches a saddle node bifurcation. Okay, this is a example from experiments from a peroxide disulfide reduction. And you see here very beautiful that the system indeed jumps from a high negative current to a low current and with some hysteresis back to the high current. The second important parameter for our evolution equation of the electrode potential is the electrolyte resistance. And now you can map out this bistable region as a function of the two parameters, the electrolyte resistance and the applied voltage. And you typically get such a, well, cusp-shaped behavior. The system would be bistable in here and monostable outside. So you can see that the larger R, the larger the bistable region in U. Okay, now the important question is, we see that if we start with the equation for the electrode potential, we need a negative differential resistance. When does it form? And here there's a beautiful work by Mark Koper, who started very simple in saying, okay, how do I describe my reaction current? That is given by, well, Faraday's constant times the number of electrons which are transferred in the reaction, the electrode area, some rate constant, which depends on phi-dl, and the concentration of an electroactive species in a very general manner. So we have seen that we need a negative Faradaic impedance. And when does it become negative? So let's form the I-reactive phi-dl of this term. So we see that we have three contributions: the change of the electrode area with phi-dl, the change of the reaction constant with our electrode potential, and the change of the concentration with the electrode potential. And all three possibilities might occur in experiments. An example where the active electrode area decreases with increasing electrode potential is, for example, a species that occurs and inhibits the reaction, and the extent of the absorption increases with increasing overpotential for the reaction. Then we would have a decreasing area with increasing overpotential. The rate constant can decrease with increasing electrode potential, either when you have as well in species which absorbs, but now the species does not completely inhibit the reaction, but it leads to a reduction of the reaction rate. For example, if you look at the reduction of metal ions in the presence of organic additives. Or you might have a catalyst on the surface for your reaction, and the catalyst desorbs as you increase the electrode potential. And that is, for example, the case for the reduction of nickel or indium on mercury in the presence of thiocyanate. And finally, the concentration might decrease with increasing phi-dl, and this is essentially due to a Frumkin effect. For example, if you think of the example I showed you before, where we had peroxo disulfate reduction, we have a highly charged electroactive species, and if the electrode potential, if the electrode has a negative charge, and you have a rather low concentration of the supporting electrolyte, the anions will be repelled with increasing driving force, with increasing electrode potential. Okay. Now, let me look at the electrode potential from a little bit different perspective. I already showed you the runaway behavior, for the unstable steady state. This can be identified actually with a positive feedback or an autocatalytic feedback. How can this be understood? Well, assume we are sitting here on our unstable steady state, and we have a small perturbation towards larger potentials. What will happen? I said, at the moment, I assume that all the other processes are very fast, then immediately the current will decrease. It adjusts adiabatically. But a decreased current will lead to a higher overpotential because you have a smaller IR drop in the electrolyte. This then leads to a further decrease in the current, and so forth. So that when you perturb the potential from this unsteady state, steady state to larger values, the system will end up on this steady state. If you perturb it to smaller values, we will end up at smaller values of phi-dl in this region here. So I could have shown also the perturbation here and here, but what you really perturb is a variable. So we have a positive feedback in autocatalytic action. I don't know, sometimes I cannot. Okay, my keyboard doesn't respond, but anyway. Okay, so now I talked about bistable system, which is the simplest manifestation of a dynamic instability, and oscillations are much more fun. So how do we get oscillations? Well, here we can look into what we know from nonlinear dynamics, and typical systems which might exhibit oscillations are activator-inhibitor systems. What do they need? This is shown here. So U is our activator, and you see that U, this plus sign, is an autocatalytic species. Now, two further conditions or requirements must be fulfilled. One requirement is that you have a second species, and the second species is activated by U. So it activates the growth of V of the inhibitor. And this species now inhibits or limits the growth rate of U. It has a negative feedback of U. So when we say we have the first ingredient from the electrode potential, namely the autocatalytic feedback of the electrode potential, which is this loop, we now need to add these two further feedbacks, the activation of the inhibitor and the inhibition of the electrode potential by the inhibitor. And actually, this can be achieved very simply, and I don't know, I have here problems. Okay, so we have our N-NDR system, and we want this negative feedback variable. And this negative feedback variable can be the concentration of the electroactive species in the case that you have a delayed transport. So if you have a slow transport, C can take the role of the inhibitor. Slow transport means that the concentration of the electroactive species in front of the electrode is given in the simplest approximation, and this is called the linear diffusion layer approximation by this following equation. So it assumes that you have a certain diffusion layer of distance extension delta, and between the electrode and delta, you always have a linear concentration profile, and for that larger than delta, you have the concentration of the bulk concentration of the electroactive species. So when C changes due to direction, it becomes smaller, for example, then immediately you have this linear profile adjusted. And if you then do your balance equation, you find that the change, the evolution equation for the concentration in front of the electrode of your electroactive species is given by, well, 2 over delta times C times K. This was a rate of your electrochemical reaction. We know this term already from our evolution equation of the electrode potential. And the second term, which simply describes the diffusion to the electrode in this assumption. Okay. Let's see why C, in fact, on the one hand, is activated by phi dl, which means that if phi dl increases, I go to larger value, also C should increase. And why C, on the other hand, leads, a large C leads to a decrease of phi dl. And so let's say this is some base current potential characteristics, and we perturb the electrode potential a little bit. We have already seen this leads to a lower current, and a lower current means that this term becomes smaller. So the decrease of C becomes less than in the original steady state, which is unstable, and C increases. So this is this positive feedback. And the negative feedback here means that if C decreases, well, then you eventually, the current increases again, and an increase in the current leads to a decrease of phi dl, because you have a larger potential drop in the electrolyte, so less drops across the interface. There is one point I should mention here, and that is this mechanism, this activator inhibitor mechanism, will only give rise to oscillations when the inhibitor equation or the change is slower than the one of the activator. So if this is very fast, we have the adiabatic, it would adiabatically adjust, and we would be back at the bistable system. But a slow change of the concentration leads to a delayed answer, a delayed response of C, and this then gives rise to oscillations. So we need some type of delay between these two equations in such a way that the inhibitor C is slower, has a slower characteristic time than our activator variable phi dl. This is again the experiment I showed you already, peroxide disulfide reduction on a silver rotating disk electrode, and changing the rotation rate changes the thickness of the announced diffusion layer, which means it changes also the time scale of the adjustment of the concentration. And for fast reaction rate, it adjusts rather quickly. And here we observe the bistable behavior. But as you lower the rotation rate and make the announced diffusion layer thicker, you observe oscillations. And these oscillations, what do they require? They only require the negative differential resistance due in the phi-dl current potential characteristics. The rest is done on the one hand by the electric circuit, by our potentiostatic conditions, and on the other hand by the slow transport. So no other requirement on the electrode kinetics. Again, in which parameter range do we expect the behavior in now our N-NDR oscillators? We have already seen how the bistable parameter range opens towards large values of U and R, and oscillations are usually found in a small loop around this cusp point. So the oscillatory region is not very large. The oscillations occur under conditions where the system is not yet bistable and occur around the branch of negative differential resistance. Note that these N-NDR oscillators never oscillate under galvanostatic conditions. So under galvanostatic conditions, you're always back to the bistable region. But of course, there are many systems which oscillate under galvanostatic conditions. And I will come back to this mechanism in a moment. But before, I should show you some experimental results that in fact, here again, we have the indium ion reduction on a mercury electrode. The form of the region in the parameter plane spanned by the resistance and U looks very similar to what is predicted from the equations. So, and this is general to all N-NDR systems, independent of the course of the NDR. Okay, now so far we discussed slow mass transport gives a necessary negative feedback to the electrode potential to cause oscillations. Are there other mechanisms? Yes. The general feature we need is that the reaction current depends on a time-dependent variable, which does not depend on the electrode potential itself. This might, for example, be an adsorbed species, which has a slow adsorption-desorption equilibrium, and the desorbed species then reacts, but this adsorption-desorption equilibrium is not dependent on the electrode potential. This would give rise to qualitatively identical bifurcation diagrams. So you do observe oscillations and bistability also in the system, provided K of phi dl, sorry, there's a mistake, the reaction current is such that you have an N-shaped current potential characteristic. Okay, what about galvanostatic oscillations? Actually, also they are found in systems which have some type of negative differential resistance. But in contrast to the N-NDR systems, here you need an additional time-dependent variable which has some potential dependence. The characteristic properties of HN-NDR oscillators, and H stands for hidden, is that The branch of interest of the stationary current potential curve has a positive slope, as indicated here. For vanishing ohmic resistance, all states on this branch are unconditionally stable. This is what we showed in the beginning, unless you have a very complicated chemistry. But so here, vanishing ohmic resistance makes a positive slope. The current oscillations that you observe for under potentiostatic conditions occur from some critical ohmic resistance on. So as soon as electrolyte resistance exceeds, or the cell resistance exceeds a critical value. And the oscillations, in fact, are the manifestation of a negative real Faradaic impedance for a finite excitation frequency omega. And how this comes about, I will show in the next slide. Important is to note that when you have such a hidden N-NDR oscillator, the system oscillates also under galvanostatic conditions, which is not possible for N-NDR oscillators. I don't know. Sometimes I have really difficulties forwarding my transparencies. I'm very sorry for that. Okay, let us see what is behind this hidden negative differential resistance. A prototypical system, and probably the easiest one, which describes HN-NDR oscillators, is shown here. So if you look now at the Faraday current, it is assumed that the current or your electrode reaction is inhibited by some adsorbed species, which has a certain potential dependence. So in the absence of the theta, you have your familiar N-shaped current potential characteristics. But now you have a second species in the electrolyte, which adsorbs on the electrode and has an isotherm that adsorption is high at low overpotentials, but it desorbs at high overpotentials. Now, when you plot the reaction current, which depends on the free area on 1 minus theta, you see that it is inhibited where you have the full coverage of your species, so it's or very low down here. And then as the species desorbs, the current increases, and then actually it starts to oscillate around this branch, because this is again our negative feedback variable. And usually you have a hard disappearance of the oscillations with very long periods, which is called a saddle loop bifurcation in nonlinear dynamics. Okay, here are the typical bifurcation diagrams of HN-NDR oscillators. You see the bistable region opens now much more strongly than in N-NDR systems towards large values of the ohmic resistance and large values of the applied potential. And you have your oscillatory regime here, and also this opens towards large values of the external resistance. So the oscillatory range of HN-NDR oscillators is much larger than that of N-NDR oscillators. Most organic, the oxidation reactions of most small organic molecules like formic acid or formaldehyde oscillate due to an HN-NDR mechanism. Okay, now I talked about simple oscillations, and we understand how they can come about by the interaction of a negative differential resistance with well, another chemical degree of freedom. What about mixed mode oscillations and chaos, more complex type of oscillations? Here we need at least 3 variables, which means 3 degrees of freedom. Okay, and they also are found pretty often in electrochemical experiments. And a beautiful example is shown here. So this is a study by Maxwell and his group on the kappa electrodissolution in phosphoric acid. And what you're seeing here is that at these parameter values, you have mainly oscillations with a large amplitude. Once in a while, there's a oscillation with a small amplitude, so which is, it is interrupted. And as a parameter is changed, the small amplitude oscillation interrupt the series of large amplitude oscillations more and more often. Here, every second large amplitude oscillation, there's a small amplitude oscillation. Here it was every third. In this lowest plate, it is every other oscillation. So you have one large, one small, one large, one small. And then the number of small oscillation increases and is interrupted by one large oscillation. So here you have 2 small, 1 large, 3 small, 1 large, and so on. So these are typical mixed mode oscillation. Mixed mode because you have these 2 oscillation modes, oscillations form of large and small oscillations, which occur in different sequences. Chaos is also seen in electrochemical systems. And an example, it's not so easy. If you have an irregular time series, well, you have to think about how to analyze your data to really prove that the data are chaotic. You're pretty much on the safe side if you observe typical scenario, as it was the case in this example, which is hydrogen oxidation in the presence of copper and anions. And here you see that we have simple periodic oscillations. And as we change, these are galvanostatic oscillations, the applied current density, you get a period 2 oscillation, and here a period 4. If you look, there are 2 different levels of the larger oscillations and 2 different levels of the smaller ones, and they finally become irregular. So this is an example of a period doubling cascade, and this usually ends in a chaotic dynamics. And also here, the dynamics might then even become more complex, and the chaotic small amplitude oscillations might be interrupted by large excursions, as shown in the remainder of the time series. So this is our phenomena that are often encountered in electrochemical dynamics. How can we understand them? We need a third variable, and actually we already have all ingredients to describe this. So let me first start with N-NDR oscillators. I emphasized that in the beginning, we made the assumption when we derived the equation for the concentration of the electroactive species at the electrode surface, that we always have a linear profile in the diffusion layer, concentration profile in the diffusion layer, which adjusts adiabatically. Now we make the second simplest or crudest discretization of the diffusion equation, which we, well, would essentially need to solve from physics, and that is we allow for a second box. So we have 2 different values here with the bulk concentration, and see 1 is given as before by a diffusion term through which it increases, and a reaction term that decreases C1, and C2 can adjust or vary due to delayed diffusion. So if the diffusion is not as fast, we have this additional degree of freedom, and when you take this into account, well, here we are. This simple well, different discretization of the concentration in the diffusion layer gives rise to mixed mode oscillations in very much the same way as I discussed it for the kappa dissolution experiment. So again, it's a transport process that is naturally in an electrochemical system, and it's not another chemical feedback mechanism you need in order to create mixed mode oscillations in N-NDR systems. What about our second oscillator, which we discussed so far? That was the hidden negative differential resistance oscillator. Here we assumed that we have a chemical species which is potential dependent and adjusts accordingly or has a slower dynamics as than the electrode potential, so that we had this typical activator inhibitor feedback loop between these two. Well, but also here we have an electroactive species C, which might be transport limited in some range. So we can now augment this term, and here I've written it in dimensionless quantity. This is why this leads a little bit, looks a little bit different to the other equations. But essentially, the third feedback mechanism in order to generate chaos and mixed mode oscillations in HN-NDR system is a slow transport of the electroactive species to the electrode. So note that this augmented HN-NDR system contains both types of oscillators. Equations 1 and 2 alone are a hidden N-shaped negative differential resistance oscillator, as we discussed it. 1 and 3 alone are the N-NDR oscillator. And if we have all three of them, well, we can get chaos and mixed mode oscillations. We have everything we need for more complex dynamics, and this is what we also observe. Again, it does not want to go forward. Okay. Now, is there anything else? Do we always require a negative differential resistance? This forms easily, we discussed, and it is a reason why electrochemical systems oscillate so easily. But there are also systems which have a chemical autocatalysis. And if everything else adjusts quickly, the chemical autocatalysis will in general give rise to bistability. And if we have a chemical autocatalysis, the electrode, you do not need for the bistability an ohmic resistance in your system. So the electrode potential in the first place degrades, let's say, to a parameter. And such systems have an S-shaped current potential curve, where now the S is due to the electrode kinetics. The bistability alone can then be described by a single variable in principle. So your chemical species, which might also be an adsorbed species, and will depend, of course, on the electrode potential as a parameter. Sorry. Don't know why this is not working as I want. Okay. The by far most prominent S-NDR system is the oxidation of carbon monoxide on platinum. Here you see a cyclic voltammogram with a beautiful bistable region, and this was obtained in a concentrated sulfuric acid electrolyte. And this system oscillates due to the Langmuir-Hinshelwood mechanism, due to the electrode kinetics. So CO dissolved in front of the electrode adsorbs on the electrode surface. You reductively you oxidize water to give an OH, adsorbed OH, and these two species finally can react to CO2, which desorbs immediately. The feedback process also requires that you have diffusion of carbon monoxide from the bulk to the surface. So these 4 reaction steps together give a positive autocatalysis. If you want to model it, you would end up with these 3 differential equations for the concentration of CO in front of the electrode, for the coverage of the electrode with carbon monoxide, and the coverage of the electrode with OH species. Okay, before I said we, in principle, or here, when I have an S-shaped negative current potential characteristics and a bistable system, as shown here, I have 1 chemical variable. Well, what I want to emphasize here is that in order to form the bistability, you only need 1 true degree of freedom. Your mechanism, as we showed it here, might require 3 variables, 3 coupled ODEs. But when you are only interested in the mechanism that creates the positive feedback, and in a simple variation, you know that you can always reduce your system of equations to a single equation. In our case, it is such that the coverage of OH remains always small in the parameter range of interest. So we don't need really to take this into account, and we can adiabatically eliminate the concentration in front of the surface. Adiabatic elimination means we need to take into account that it changes, but we can assume it changes quickly enough so that we can finally, or in a reduced way, or in the most efficient way, write the equations only for the coverage of the electrode with carbon monoxide. So in this way, it is to be understood that we need only 1 variable. Okay, what happens if we have an S-NDR system, a chemical bistability, and we happen to have some IR drop in the electrolyte we cannot compensate? Well, then actually we have a small correction at this lower part of the negative differential branch, and a large correction where we have a large current. And in this case, we don't form the bistable region, but we unfold it. We get a curve which becomes monostable. Is it really monostable? Well, to see this, we should again do or perform a stability analysis of our system. And we know that we do have negative Faradaic resistance underlying this branch. And in this case, you can see that if you add the equation for the electrode potential, this makes a negative feedback loop. And these 2 together always produce an activator-inhibitor type of system. Does it oscillate? It might be, but not very often. And now, to understand this, you have to remember what I said. When do activator-inhibitor systems oscillate? Whenever the inhibitor has a slower time scale than the activator. In general, the electrode potential is a fast variable. So it has the time scale separation will not be given. Usually this is faster than the typical time scale of changes of a chemical variable. However, if we have very large electrodes, or for some other reason, a very large capacitance, you might lower the capacitance of your system. So the time scale might get a very slow response of the electrode potential, and S-NDR systems might oscillate. And there are some reports on oscillations where we have very large fuel cell type electrodes, which claim that the oscillations are due to an S-shaped current potential characteristic. In this case, the typical bifurcation diagram in our two electrical parameters, our omega and u, looks as shown here. So we have a rather or a smaller bistable region now at low values of our omega and low over values of the applied potential, which has again this cusp shape and closes at some critical value of the electrolyte resistance. And above this region or this resistance, you have a huge oscillatory region. But remember, only if the electrode potential is reacts sufficiently slow, which means if the capacitance is sufficiently large. Okay, finally, we have a third type of oscillator in electrochemical systems, and these are so-called strictly potentiostatic oscillators. And here you have an S-NDR system, which means you have a chemical autocatalytic system and a feedback through a chemical variable. And in the case of the C oxidation on platinum, what is sufficient to drive the bistable system into oscillation, which oscillate under for constant value of the electrode potential, is that you have a reversible adsorption and desorption of some species, for example, an halide ion, chloride or bromide or whatever, which inhibits the adsorption of carbon monoxide. This is all you need. And then you obtain also strictly potentiostatic oscillations. Okay, now we discussed how oscillations emerge in electrochemical systems. From a universal point of view, we can say, okay, we have essentially three different types of activator-inhibitor interactions. We have hidden negative N-shaped negative differential resistance oscillator or N-shaped negative differential resistance oscillators, in which case the electrode potential is a positive feedback variable, acts like the activator, and the negative feedback variable is a chemical variable, and here a slow transport to the electrode is sufficient to make the system oscillate, at least in the for the N-NDR oscillator. They are very numerous. So most of the electrochemical systems oscillate or can be characterized as an HN or an N-NDR oscillator. Then there are some S-NDR systems and oscillators which are rare, and I already said why they are rare, because the electrode potential is usually a fast variable, not a slow variable. But here the the positive feedback variable is a chemical variable, and our negative feedback variable is the electrode potential. And finally, we might also have a chemical mechanism, meaning two chemical variables for both feedback loops or feedback variables, activator and inhibitor. These are the strictly potentiostatic oscillators. Okay, here I would like to ask whether you have any questions so far, because I will then talk about spatial patterns and see when our electrochemical systems might form patterns, waves, turbulence, whatever, what destabilizes the spatial uniform system. And why it is nevertheless often spatially uniform, so that we can observe macroscopic oscillations. So are there any questions?
Thank you, Katharina. Maybe we can switch to questions. If anyone has any questions, you can directly ask. And if you can also leave your questions in the chat, and please stay online, so we will have a second part of the talk.
Okay, wait a moment. So then if there is no question for the moment.
Okay, maybe I can start because normally
Okay.
that's our audience is not always active at the beginning. Okay, Martin, go ahead.
Thank you for a lovely introduction to oscillators, Katharina. I had a question. So with the chaotic systems, we often get noisy electrochemical data. And looking at the current, is there a test one would potentially do to tell the difference between a noisy electrochemical system and one that's actually either a coupled oscillator or a chaotic system that you could suggest for analyzing the data?
Okay, yeah, there are some easy methods that give at least a good hint whether your system is chaotic or noisy. And one is that you determine the maxima of your oscillating time series and you plot one maximum versus a previous maximum.
Yeah.
And if you do so and you obtain well, essentially a unimodal curve, then it's very likely that you have chaos. This would mean that your underlying map dynamics, I mean time discrete dynamics, is equivalent to the dynamics you find in the logistic map.
Yeah.
Another thing you can do is what I showed in the beginning as for the example of chaos, that you plot the value of your current or whatever you measure at time t versus the value at time t minus tau and maybe also t minus 2 tau, where tau is a time delay and should be approximately 1/4 of a period. And then you obtain a beautiful chaotic attractor in phase space with some structure, whereas when you have high dimensional disorder or noise, it looks like, well, it fills your phase space completely. There's no structure. This would be two very simple indications whether you have chaos or not. Of course, you can also obtain more quantitative measures like the Lyapunov exponent. You need a positive Lyapunov exponent, which is not easy to do for experimental data. And this requires the phase space reconstruction, as I said, and then some techniques which can be found in the literature that you look at the separation of close by points in phase space. But my experience is that this is it is very easy to obtain or to do mistakes in the choice of the parameters when you do this, try to extract Lyapunov exponents from chaotic data. So it's much easier to get some qualitative indication than this quantitative measures of your chaos.
Cool, thank you.
Zahur?
Thanks, Andrew, for arranging this nice meeting with Professor Katharina. I'm pronouncing your name correctly, Professor?
Yeah, perfect.
Okay, thank you. So my question is related to like you explained. I joined late, I think maybe 15 minutes late, so maybe I was unable to understand some part of the lecture. So quick question is that if we have oscillation is only current density based, or it can be potential based also, like all the oscillators that you explain, you give examples from literature that have currents that oscillate with respect to time or current density. J is current density here. So you think the similar behavior we can observe potential with respect to time?
Galvanostatic oscillations, yes.
Yeah, we can observe. Yeah.
The what I called hidden negative N-shaped negative differential resistance oscillators, they oscillate galvanostatically. And S-NDR oscillators, well, actually, I would not say that we come to the S-NDR oscillators under galvanostatic conditions again. They might oscillate, but what you very easily get is a spatial instability when you have galvanostatic conditions for S-shaped NDR systems. So if you observe oscillations with an S-NDR oscillator, they are most likely non-uniform.
Oh,
So you have a spatial temporal wave, not
thank
uniform
you.
oscillations.
My work is related to rechargeable lithium-ion batteries, where we have similar kind of behavior during charging and discharging, unless there is some perturbation observed. If so, that's rare. We observe.
Okay,
Yeah.
actually, this is a very interesting one. So you observe oscillations during charging and discharging, right?
Yeah.
Okay. In your case, I think I'm absolutely no expert in batteries, but I looked into these instabilities a little bit, and you have these phase transition cathodes, I think, where your lithium ions can be in two phases.
Yeah.
And this, well, is a first order phase transition system, very similar to an S-shaped, yes, bistable system. And so what you have then is you have coupled bistable systems, many coupled bistable systems, which are individual and under galvanostatic oscillations, one after the other switches into the other state. And we have shown that if you take S-NDR systems and couple these bistable units, really small electrodes, individual electrodes, then the coupling might induce oscillations of the different groups.
Yeah.
I will not come to this point today because this is rather complicated, I have to say, from the theoretical point of view to understand it. But there is a lot of room for further investigations and for instabilities in such coupled bistable systems. And there must not be any, so the feedback in this case must not come from a second species, but can come from the two domains which form and interact with each other.
Okay, thank you. So what we call the second species, is this the electrolyte, the species?
No, this was my second variable, which means either, for example, the concentration of the electroactive species in front of the electrode, or the coverage of the electrode with some species which interacts with the reaction, which might inhibit the reaction in the HN-NDR oscillator, and so on.
And one last question, do you allow me to ask from Professor Katharina? And this is because my work, my master degree was on quantum plasmas, but my PhD is both in physics and chemistry, where I work on electrochemistry. Now I'm electrochemist working in UK battery industry. So we are investigating some R&D. So I'm trying to connect like these equations with Maxwellian, because they are charged when you have these kind of oscillations, as you explained. So S kind can be simple harmonic oscillators like we have in quantum systems. What you think like, and we can combine them with Maxwell equation because they have charge on them. We can't ignore the charge behavior of the whole system. If we say like, if we have cathode and anode in a full battery system where we have even charges on the electrolyte as well, you have the lithium ions or any species ions, they move from positive charge gradients to negative charge gradients. So there's a charge gradient as well, concentration gradient as well. There's temperature also, and there is fields also. We can't ignore. So it's quite complex system, to my understanding.
Well, okay. When you say there's a charge gradient, usually your electrolyte is as electroneutral as possible. So it adjusts rather quickly to an electroneutral state, and where we have charges, I call double layer. And I mean, the double layer dynamics I discussed, and they incorporate the charge. And when we do our spatial modeling, we mainly assume that the electrolyte is electroneutral, and the potential distribution in the electrolyte can be described by Laplace equation. Of course, if you have different double layer drops at different positions of your electrode, then you get a non-uniform potential distribution in parallel to the electrode. And this you should take into account. This is a so-called migration coupling. I will very shortly talk on this, and this is a very effective coupling in the system.
Thank you
of the
so
different
much.
parts.
Yeah, thank you. Yeah, thank you so much for your answer. Yeah, it's convincing. Yeah. Thank you.
Thanks, Katharina. Can I ask maybe one or two general questions, and then we will
Sure.
proceed? So one is related to the two diffusion layer system that you showed for, I think, a copper.
Yes, this was set up by Copper.
It was, we could see the beating basically of these oscillations that changed the period. So to me, it looks like quite a lot like the way, say, our heart works and the way the neurons communicate. So the way that the action potential oscillates and then it spikes at some point and it keeps oscillating. So are there any indications that indeed similar processes are what actually drives the neuron communication?
It depends on the level on which you want to describe it. But if you remember my introduction where I said it was absolutely remarkable that Bonhoeffer and Frank, and even before Ostwald and Heathcote, studied waves on the iron wire in order to understand nerve impulse propagation. This was exactly the idea, because they said the electrical signal from the electrochemical experiment looks so similar to signals from the nerve impulse propagation. And yes, from many basic principles like this simple activator inhibitor system I showed you. I mean, nerve impulse propagation is often excitable, but anyway, yes, these are the universal aspects of nonlinear dynamics, and electrochemical systems actually helped a lot to study some or validate some theories in nonlinear dynamics of basic principles leading to certain dynamic phenomena.
Okay.
So the question is, there are certainly similarities, and this is also why I don't know whether I got it really across or not, but that you should try to reduce the system once you have resolved your electrochemical mechanism, like in the CO system, where I ended up with 3 equations and it was not so clear where the feedback is, to reduce it further and to look from a mathematical point of view at the system or at the structure of the equation and analyze the feedbacks in there.
So
and then
in other words,
can understand what your system, which dynamic phenomena might occur in your system.
I see. So it's quite likely that something can be reduced to such processes, but it's just not that easy at this point. So, but the fact that we see this beatings and so on, so it's quite likely that it's driven by similar, generally on the theory level, similar processes.
Biodynamics, which is the same that underlies, I mean, to some extent, it depends on how deep you go into the nerve impulse propagation. I mean, but the principles or some features have the same explanation. I mean, if you look at the Fitzhugh-Nagumo system, which is a very a strong simplification, but for the nerve impulse propagation, it's exactly such an activator inhibitor system.
Okay, and the other question was about the facet dependence. So for copper, is there any, so if we say look at different facets, do we expect then the system will be very different because the absorption will be different as it's facet dependence? Or it's not something that people normally look at?
There have been some studies on, now I have to remember correctly, oscillations of formic acid, I think, of different facets. And also we did it with a CO oxidation in the presence of halides. And yes, the facets lead phenomenologically to different shapes of the oscillations. And in some instances, there are even facets that don't oscillate. So for example, I remember that also the hydrogen oxidation in the presence of poisons like copper and chlorides, this is an HN-NDR oscillator, on platinum oscillated on platinum 111 and platinum 100 and not on platinum 110. I hope it was.
Okay.
I might get it wrong, but it didn't oscillate on one of the facets.
So there should be a pretty good sensitivity, noticeable sensitivity to the facets. So does it mean that in general, these oscillations, they can be used to have a very fine probe into the surface dynamics? I think this is where I'm trying to lead to ultimately.
Yes and no. No, because your main variable, which dictates, I would say, the dynamics, is still the electrode potential. And the electrode potential couples very strongly different parts of the electrode together. And then the facets might simply be driven that are non-oscillating by the oscillating part. And it's very, I mean, if you have a polycrystalline surface, and you would, yeah, I mean, I think Hamilton Varela has nice work where he used really single crystal or oscillations to show differences in the reactivity of single crystal surfaces as a kind of probe. But I'm not sure whether this is can be generally used or is a lucky coincidence.
Okay, that's good to know. Okay, yeah, I think I know that paper. Okay, thank you. Maybe we can proceed.
Okay, then I should share my screen again. So now I need to see where I was. Okay. So what about spatial patterns? So far, we looked at the lumped system and simply assumed the surface reacts uniformly. But we know from other chemical systems, from the Bézier reaction, for example, Bézier is Belousov-Jabotinsky reaction, which is probably the most famous oscillating chemical reaction, but also from heterogeneous catalysis and at foremost the work by Gerhard Ertl and Butch Rotermund at the Fritz Haber Institute, that beautiful patterns might form if you have dynamic instability in the system. So, and these patterns can be described, or patterns in chemical systems, biological systems, and also biochemical systems were mainly described by what is called a reaction diffusion equation, which looks like that. So here U would be our variables in the system, and lambda parameter. So far we only looked at the dynamics of the uniform system F of U and T, and now we say, okay, we have an extended system and we couple the different parts of the electrode by a diffusion term. So this is a Laplace operator and D diagonal matrix to make it not too complicated. And such systems very easily give rise to spiral dynamics if F of U has some oscillatory or excitable dynamics. And they can also be found in electrochemical systems. And there's, well, very beautiful work by Ivan Krastev and co-workers and colleagues from Bulgaria on the deposition of alloys, which might form these spiral waves. But in our case, we have to see how can we incorporate the electrode potential into this framework of reaction diffusion equations. And here, actually, things are not that simple. And in one of the questions, I already answered what you have to do. You have to look at the potential distribution within the electrolyte, because in our local dynamics depends also on the potential drop within the electrolyte. And in order to describe the obtain the correct equation or formulation for the electrode potential and this for the spatially extended electrode, you have to describe or to solve the Laplace equation within the electrolyte with boundary conditions on the counter electrode or far away, that you assume that you have somewhere equipotential curve. And then you have your pattern in phi dl at the electrode, because phi dl is our autocatalytic variable. If we expect patterns, you should have some variations of the electrode potential lateral to the electrode. And this would be the second boundary condition for the Laplace equation. And well, the other ones you can choose as zero flux boundary conditions. This makes it rather complicated. You do get then an equation, you can extract it or formulate it for the double layer potential in a closed way. I'm not doing it here because it is mathematically a little bit involved, and I don't think we have so much time, and it's worth going through it in such a rather, well, for this type, rather short tutorial type of lecture. But what you arrive at is a reaction migration equation for, or what we call reaction migration equation for the evolution of the double layer potential. What is important is, what difference does it make that we have a reaction migration and not a reaction diffusion equation? And diffusion equation is always a local coupling, so it's a next neighbor coupling. The reaction migration equation has a non-local coupling, or describes a spatial non-local coupling, which means that if at some point on your originally uniform electrode you have a perturbation, this perturbation is immediately felt by a whole range of positions, adjacent positions with different strengths. Non-local means it decays in strength, but it's an entire range. And this property dictates, on the one hand, the spatial extension of the pattern, or makes at least typical electrochemical waves of the type of HN-NDR systems or N-NDR systems much larger, also in S-NDR systems, by the way, than in chemical systems. So when you think of the spiral wave, I showed you the wavelengths of the arms were about 20 micrometers, this range. Typically in electrochemical systems, you have a millimeter, or at least 100 micrometer, millimeter, or even larger. And this is due to a very effective coupling, non-local coupling through the electrode potential. And this effective coupling in many situations also leads to stabilization of the uniform electrode surface and to a synchronization of the entire surface, which answers the question I posed initially: why do we observe in very undefined systems or on undefined electrodes like this helical bent platinum wire a large global oscillation? So we have reaction migration equations that lead to a spatial non-local coupling. The spatial non-local coupling in HN-NDR systems tend to act towards a uniform surface, and what you observe, and what was rather spectacular when it was first seen, is that the motion of fronts is accelerated in time. And this you can see in this picture, that you have in a bistable system now here a small nucleus of the other phase, and this nucleus spreads in a faster and faster manner. In S-NDR systems, the spatial coupling, this long-range coupling, destabilizes the uniform state. So S-NDR systems very easily form patterns. And so it's more likely that an S-NDR system is in a patterned and non-uniform state, not because you have any inhomogeneities or heterogeneities in the electrode, but from the interaction of the local dynamics with the migration coupling. And what will form easily in S-NDR systems are Turing type patterns, which are stationary patterns with a characteristic wavelength. However, again, the wavelength is rather large compared to other chemical systems of the order of millimeter due to the long range of the coupling. But the long range is also exactly what you need in this case for a Turing instability. Okay, now this part was rather short and imprecise, I would say, qualitative, phenomenological, what I told you, because I cannot cover everything in this lecture, and the most important coupling in electrochemical system, which gives rise to spatial instabilities, is actually not the migration coupling. It's not the diffusion coupling from chemical species, which you also have, of course, but it's a global coupling. And the global coupling is, again, intrinsic from the electrical properties of your system. And so in electrochemical systems, spatial instabilities and patterns are predominantly caused by a global coupling. And there are two types of global coupling, or two types of operation modes that induce a global coupling. One is if you have an external resistance or external resistor or galvanostatic operation mode. So every galvanostatically performed experiment has a strong positive global coupling. And also when you use a lock-in capillary and bring your reference electrode close to the working electrode in order to minimize the ohmic resistance, which usually is not wanted, you introduce a negative global coupling. And both global couplings might lead to spatial instabilities. The negative global coupling is very destabilizing under many conditions. A positive global coupling leads to spatial instabilities. I will discuss this a little bit further for S-NDR systems and for relaxational oscillations. So if your oscillations have strong relaxational character and are operated under galvanostatic conditions, it's very likely that parts of the electrode will form, for example, an antiphase cluster. Okay, so how is a global coupling defined and described in the medium? Well, global coupling means that the dynamics at one position of your system depends on the mean value of one variable. And this is how I denote the mean value in my equations with these angular brackets. And this x in this equation denotes that I integrate over the electrode surface. So this is, well, taking the mean. And you can always formulate the impact of the mean value of your of the global quantity on the local dynamics in a way that this impact vanishes in a uniform situation, meaning as it is done here. So you would have a coupling strength gamma and the difference between the mean and the local value. Now let us see what does positive and negative mean. Positive and negative, first of all, is a sign here. And if you see what happens or what this coupling term, global coupling term, does with a small perturbation in these two systems, you can already see that the negative global coupling has a very destabilizing action. So assume that you have some perturbation in phi-dl such that phi-dl or the electrode potential is larger than the mean electrode potential. Then this term will be negative. And a negative global coupling means you have a negative gamma, a negative coupling strength, which means this term, the total term is positive, and your perturbation to larger values of the electrode potential will be enhanced. And only at this position, where the electrode potential is already a little bit larger than the average, it will be pushed to even larger values. And if it was a little bit smaller through a fluctuation, it is pushed to even smaller values. The positive global coupling obviously does the opposite and is damping, but as I said, it is only acting stabilizing for if phi dl is an activator. So for N-type negative differential resistance systems. And it might still, in this case, lead to patterns, but then it destabilizes oscillations, not uniform steady states, not steady states. So uniform oscillations, but not steady states. Okay, now let us see how how we can understand these two ways in which in electrochemical systems global coupling can emerge. Well, let us assume the following. We have our spatially extended electrode, and now we want to exclude all lateral interactions through migration coupling. So we assume we slice our electrode in very small portions, which are isolated also through the electrolyte. So we have an equivalent circuit as shown here, where one of these units is composed of the interfacial circuit, and now I separate or divide the electrolyte resistance between the working electrode and the counter electrode in the compensated part and uncompensated part. So my reference electrode would be at this point, and I assume that the reference electrode has the same distance to all positions of the electrode, which is hypothetically for most electrode geometries, but you might realize it, for example, with a ring-shaped electrode, with a ring electrode, where you put the reference electrode on the axis of the ring. Okay, then your potentiostatic control can be expressed as being that the set potential is equal to the average of the double layer potentials. The average potential drops across these individual uncompensated parts of the resistance, which is called here delta phi I, and the potential drop across an external resistance. And here it's clear, here I is the average current, that this also gives a feedback or contains a global quantity. Now, let us first look at the impact of the compensated resistance. So at the moment I neglect Rx, and now you write these individual resistances as the total uncompensated or compensated resistance Ru and Rc. And if you then solve for this equivalent circuit, the dynamics for the electrode potential or the potential drop across the double layer of an individual unit, you end up with this expression. So you see that we have here the difference of the electrode potential of an individual unit from the mean, and we have a coupling strength, which is the larger the compensated resistance is, so the smaller Ru is, and we have a negative sign. So if I have a strong compensation of my cell resistance, I introduce a negative global coupling, a destabilizing global coupling, and under these conditions you get, it's very easy, your electrode will slip into some pattern. So you have a global destabilization of the uniform state. On the other hand, if we now neglect or assume that we have no compensation, that we have the entire cell resistance, but so Rc is 0, but we only have the external resistance, then we obtain an equation for the circuit, which looks very similar to our other system. We now see that the larger Rx, the stronger is the coupling, which is intuitive somehow. And if you compare this expression with the other one, you see that that I obtained for the in the presence of some uncompensated resistance, you see that the external resistor with a an external resistor with a negative impedance acts exactly in the same way as an external resistor. Sorry, this is as the compensated resistance in before. With other words, if we would have here a negative impedance device which would give rise or act like a negative resistor, we would obtain the same dynamics as we do when we compensate part of the cell resistance. And actually, this is exactly also what you do when you compensate it or use your potentiostat to compensate part of the cell resistance. So this, and the negative resistor or impedance, of course, changes the sign of this term. Okay. What is important to note is an external resistor might be some artificial construction. Sometimes in some semiconductors or whatever, you cannot avoid some series resistance, but this case is mainly important to look at galvanostatic conditions, because under galvanostatic, or you can understand galvanostatic conditions as a limit of potentiostatic conditions with an external resistor and the external resistance and the voltage going to infinity. So any galvanostatically operated system has a strong positive global coupling. Okay, now here's hopefully some fun. These are some patterns which emerge due to a negative global coupling in an HN-NDR system. This is again the hydrogen oxidation on platinum in the presence of copper ion. And what you see here is that an active domain rotates around a ring electrode in a rather constant manner, and you get in the current response some oscillations. The oscillations here are probably mainly due to some inhomogeneities in the width of the ring, and the dynamic would be for a perfectly uniform ring completely stationary. Okay, but when you change the parameters, the pattern becomes more complex. And you see that now we have really a center from which approximately here a wave emerges, and it now expands in both directions. See it in a moment. And then the wave splits. We have a cone which is left on one side, and on the other side it travels around. And this goes on in a periodic manner. So this is called an asymmetric target pattern. And actually, using the dynamics of the hydrogen oxidation on platinum, together with the global coupling and actually also our migration coupling, we could exactly reproduce this type of peculiar target patterns. But the dynamics can become even more complex. Here you see a situation where we have a cone, and from the cone, the cone stays and starts to oscillate and sends out waves in one direction, and the oscillations become larger. And you see that we also have rather irregular current time series. And now we have a state which is similar to the pulse state we saw on the left picture here. And goes on. And now, all in a sudden, the electrode is completely activated, deactivated, and the entire scenario starts again. That you have first target patterns, then asymmetric target patterns, pulse patterns, and a burst. So such complex time series must not always come from a complex local dynamics, but it might also be induced by spatial patterns. Okay, the last aspect I want to discuss today are galvanostatic conditions in an S-NDR system, the galvanostatic control. And we have seen that the galvanostatic control introduces strong global, positive global coupling. And why is the S system pretty interesting? Well, if you think again of the CO oxidation system, we have here a low current state, which is CO covered. We have a high current state, and under potentiostatic conditions, we can only realize here either this high CO coverage or a nearly empty electrode, but no states with an intermediate coverage, which would like on this negative differential branch. But this is not accessible under potentiostatic conditions. Now you might say, okay, why not assessing this branch by adjusting the current density approximately? Go to galvanostatic conditions. Well, let's see what will happen if you set your system on such a state, and then you have a small fluctuation in the coverage. So the coverage becomes a little bit smaller from this state on than the equilibrium coverage. Then your local dynamics will drive the system in the high current state. Okay, you say it's not possible because then the galvanostatically set current is not equal to the actual current. Well, if this is not so, what will the potentiostat do? It will shift the system to a smaller electrode potential. So when it was initially here, we were driven into the middle region of the bistable system, where both of our bistable states are equally stable. And so the system will adjust a state here where and the ratio of the electrode which are in the low or in the high current state adjusts such that the set electrode, the set current is always attained. So also under galvanostatic conditions, to sum up, you cannot access this negative differential resistance branch. Rather, the electrode will split into two domains. One domain is in one of the two stable states from your underlying potentiostatic system, and the other domain in the other one. Actually, this is very similar to what is seen in phase transition systems, in equilibrium phase transition systems of first order, when you have the coexistence between two phases. And finding the equistability potential would be something that is equivalent to a Maxwell construction. And in fact, if you do simulations of an S-NDR systems and look which stable states will the system attain and which bifurcations do you have, you exactly predict what I kind of explained here, what one would expect. You have your stable uniform state, but when you enter the negative differential resistance region, the state, becomes unstable and your potential jumps to a value in the middle of your bistable region. And as you further increase the current density, you stay here until you jump back when you come outside this region on your on the second branch. And in fact, this has been also observed experimentally. Here you have, for the C oxidation again, I said this is a prototypical S-NDR system. Galvanostatic current potential pairs which were measured, and they are stationary. These blue points are measuring points. This is the cyclic voltammogram under potential control. And you see that under galvanostatic conditions, the potential is, or a potential adjust, which is nearly independent of the set current density. And if you look at the electrode as a spatially extended medium, you see that yes, in fact, the electrode splits in two different domains, one CO-covered domain, which is red here, and this was done with spatially resolved FTIR spectroscopy, and another empty domain, which is shown in blue. And as you increase the current density, the relative sizes of these domains adjust such that the set current density can be maintained. Okay, with this, I would like to end my talk and summarize shortly a few points about patterns in electrochemical systems from my second part. So most patterns are due to the coupling through the electric potential. Coupling through your chemical variables are less important. And there are two principal mechanisms how the electrode potential, the different sides of the electrode are coupled through the electric potential. One is the migration coupling through the electrolyte, the electrostatic potential in the electrolyte, which is non-local. The other one is a global coupling, and the global coupling can be due to an external resistance or galvanostatic control of the electrochemical reaction, or it can be due to a compensated cell resistance. And with this, I would like to thank you for your attention, for staying so long at a, well, late afternoon before a holiday, at least here in Germany, and I think in large parts of Europe. We have a holiday tomorrow and also for Easter Monday. And yeah, I stop my sharing and I'm happy to answer further questions.
Thank you so much. Please feel free to ask your questions. I think you can unmute yourself now. If we have any questions, of course. Yes, Martin, go ahead.
Hey, Katharina, again, a lovely talk, and I really enjoyed hearing about this stuff. You make it sound like sort of electrochemical dynamics and oscillations and so on are almost all solved. Are there any big open questions, or what directions is maybe the field moving towards? And is it all applying it to systems, or are there frontiers that are being pushed that maybe we didn't hear about today?
Okay, of course, if you design such a talk, you present it, what is understood. Okay, yes. I think a lot of questions are not understood. This relates essentially to patterns during corrosion. I could have shown you some very unusual spiral waves which were observed in corrosion experiments, and the dynamics of corrosion, the dynamic instabilities in metal corrosion are really still an unsolved problem to a large part, not completely. We ourselves work on the silicon electrode solution, which we take as a model system to look at very okay, what we study are coupled amplitude oscillators with a non-linear coupling. Okay, so let me say a few more words. This is a photoelectrochemical system. So we also have the illumination, which means that now the coupling in the semiconductor is through the diffusion and migration, the transport or flux of the holes in the gradient of the electrochemical potential. And this destabilizes the system and leads to a huge amount of patterns which help understand which patterns might emerge in general in systems with non-linear coupling, I mean, this is not so easy to understand. Essentially, you can say that the mean, it's a global coupling, and the mean or the order parameter enters the equation with some nonlinearity. So, for example, a cubic term, phi to the power of 3. And what we found there was that clusters or domains formed spontaneously, which oscillated with different frequencies. So these are multi-frequency clusters. And multi-frequency clusters occur in adaptive systems. Adaptive systems means that you have a type of coupling where the coupling strength adjusts and depends on the state of the system. And here we are back to Andrew's question before. Can we link this somehow to patterns of nerve impulse propagation? Here we can map this to neural networks where the adaptive neural networks. And I think that this is a very important question where we really can understand in a physical experiment, I mean a real experiment, how an adaptation could work. And I think also that here the electric potential is a very important quantity that enables, so due to this long-range coupling, such an adaptation, and due to the fact that you have to consider the gradient of the electrochemical potential, meaning that both gradients in C, which is here the concentration of the holes, as well as of the electrostatic potential play a role. And this might be very well the case in neurology. Okay, now I had some more examples in mind I want to give you, but now I lost my thread somehow. But yes, I mean, there are still many systems that are not understood and probably interesting to understand from an electrochemical point of view. And then there is this type of experiments you can do to understand better certain dynamic regimes from the nonlinear dynamics perspective, where we want to learn universal laws for pattern formation.
So, Katharina, does it mean that in principle, these electrochemical reactions and in these kind of experiments can be used to model or to probe, I would say, certain models in experiments, but those certain models can be completely unrelated to electrochemistry at the beginning?
I mean, for example, what might be some outcome. I mean, as I said, we are just working on this multi-frequency clusters. We are very excited about them, and now we derive the equations first from the physical dynamics, but then we try to extract from there which ingredients are really necessary to lead to the adaptation of the coupling strength. And this then can feed back to other systems where people might see, okay, yes, I have the same setting, and I might expect multi-frequency clusters or other types of adaptive or other manifestation of an adaptive coupling.
Okay, I'm also curious about something that might be a bit obvious, but maybe you can just leave your comment on that. So from what I see, most of your presentation was about how we can interpret the oscillations, how we can model the oscillations, and then see in experiments. But can we really backtrack, going backwards? So we see some oscillations, we do certain experiments, we see them, we record them, and then we fit them using the certain model, and then extract from that model the parameters that we cannot obtain otherwise about the electrochemical system. Or it would be difficult to obtain through, say, impedance or some other techniques.
Very interesting question. Very difficult to answer.
So people do not do it normally. As I haven't seen too many. Usually, from my perspective, at least, when I see the papers about these oscillatory reactions, they just usually report the oscillations and probably the model that can describe them. But it's not like they use these oscillatory reactions to probe the electrochemical system itself, to extract certain quantities that are of interest, maybe for some other things.
Yeah, I mean, you need to have some good understanding of the underlying mechanism in order then to retrieve the parameters. Or I think it can and has been done in some instances, but at the moment I cannot come up with a good example. I think it's not very common to do so, and not possible in many situations, I would say.
It's because the systems are not well defined, or it's because there are certain things that we just cannot account for mathematically. So if we have a perfectly
I mean,
defined
usually you
system,
have a rather rough description. And you saw, for example, let's start with the simplest system I introduced, which was a bistable N-NDR system.
Yes.
So what do we need, or what we might learn is, yes, we have a negative differential resistance. In this case, you can also get it in another way. This is clear. But the question then, what is the origin of the negative differential resistance, is already more complicated. I mean, from the dynamics, you cannot distinguish whether the area decreases with increasing electrode potential, or whether it's a rate constant, or whether it's a concentration in front of the electrode. Because all of them have the same mathematical influence or impact on the system. On the other hand, I mean, what you can easily say is, okay, I have a hidden negative differential resistance, very likely if I have if I observe galvanostatic oscillations, and you know it's now not a S-NDR system. You should also be careful doing this, because then you assume a uniform electrode. As soon as you have pattern formation, everything breaks down. I mean, or at least it is much more complicated than to extract parameters from your nonlinear dynamic measurements.
Okay, so far it works only in one direction when we can first simulate.
Mainly. As I said, there are other studies, and I think who used this really as a sensor was Hamilton Varela. But I can at the moment not recall the system he used. But
other examples from go ahead. No.
Yeah. No. It's
other examples from the surface science, maybe in catalysis, not electrochemical, but the gas phase, gas solid interfaces, maybe because it's simpler to solve.
Yeah, it is simpler, but still, I mean, okay, let's again use as an example the oxidation on platinum as studied in Ertel's group. So he studied it on different single crystal surfaces like platinum 110, platinum 100, and platinum 111. So the dynamic behavior of all three single crystals is very different. Platinum 111 does not oscillate, it shows only bistable behavior. The other two do oscillate, but platinum 110 shows much richer behavior than 100. Okay, so you would think you can learn something, right? Taking a polycrystalline platinum electrode, you still have oscillatory behavior. So, I mean, you have to know your system very well to understand which parameter you really could extract from the dynamics, from the oscillatory dynamics.
Okay, well, hopefully
so I mean, yeah.
May I ask one more question? So perhaps a rephrasing of what I was asking before, but experimentally, I see an oscillator in my system. Is there a good test or a way to know without direct observation whether I'm getting spatial oscillations, or whether I can get away with sort of, can all spatial oscillators be summarized as a simple two variable or one variable kind of oscillator, or is there something about the behavior that I can analyze the data to get at?
Okay. To answer, I mean, with the spatial patterns is a little bit more complicated. Well, it's seldom that you really look spatially resolved on your electrode surface, but what you can do is, first, you could, for example, vary U and R in your system, and you can use an external R, and then you can see very quickly whether you have one of the characteristic bifurcation diagrams I showed you, which are different for the different types of oscillators. How to see whether there is a spatial instability from a global time series? This is what you have.
Yeah, and the answer may be we don't have a way, but I'm just thinking if I
data. I hesitate a little bit to say there is no way because I might not think of it at the moment, but it's certainly not that simple.
Sure.
So I'm not aware, how you could prove it easily.
Yeah, Martin, do you have any more questions, or should we?
Maybe one more. Sorry, I'm taking so much of your time.
No.
Holiday tomorrow for you guys. So a lot of the oscillations you've shown have been relatively low frequency, either spatially or temporally. And spatially, you sort of explain that that's for electrochemical systems, that's expected. For the temporal oscillations, is it a matter of the observations are sampling at relatively low frequencies, so that's where people most often observe oscillations, or is there other physical phenomena that have certain temporal scales, and that's why
yes, you have certain time scales in the system.
Yeah.
And essentially, that is a little bit oversimplified, but it's the time scale of your inhibitory variable, which dictates the time scale of the oscillations. Yeah. It's too simple, but the negative feedback, which is a little bit delayed, I said that the activator is always a bit faster, gives you the time scale of oscillations. And in electrochemical systems, you might have oscillations from millihertz to 10, 20 seconds.
Yeah. Okay.
Yeah. So what's not millihertz, kilohertz, I wanted to say. Okay. Kilohertz to millihertz.
Yeah.
Roughly. They are very slow oscillators and very fast ones, but not much faster than kilohertz.
Yeah, I was just wondering if there'd be ones that we didn't see because we're sampling too slowly or things like that.
Yeah, but if you think of the mechanism which leads to the oscillation and you understand a little bit of the time scale of the reactions, I think this is a reason. It's not to be expected that we have oscillations in the microsecond range.
Yeah, that's what I was trying to think through quickly when the equations came up, but I figured you'd spend more time.
Yeah, and also, I mean, in the brain, the communication through electrochemical signals is slow. It's milliseconds.
Yeah. Thank you.
All right. Katharina, thank you so much. It was an amazing, really long talk and discussion. I think we've learned a lot about this field, and it looks like this field has, well, it's been around for a long time, but still there's so many gaps and so many things that we can explore. So hopefully there will be a lot more audience and from some time down the road.
Well,
so thank you so much
very much for the invitation. Thank everybody for joining, and goodbye.
Thank you. Bye-bye.